Hey guys, I'm Anand and welcome back to today's video. And today we're going to be starting a new calculus series, and in this calculus series I'm going to go through all the topics in calculus 1, calculus 2, or calculus A, B, and BC. Today's topic is limits and also defining what it means to be continuous. So obviously if we're going to start with something, we need a definition of it, and what we need to think about before we get to the rigorous parts of this definition is conceptualizing it. What a limit is what happens to a function as it approaches some value. So as x approaches some value of a, then we can say that f of x approaches L. What does that mean? As x gets arbitrarily close to a, like as close and close as close, f of x get closer and closer and closer to L. So how can we quantify this? How can we make this something, a provable fact? Okay? Think about it like this, okay? We need f of x to get as close to L as we want, right? If we want it to be within 3 of L, then we want that to happen because we know for a fact that if it approaches it, then we have to be able to get as close as we want it to that point. So we need f of x to get as close to L as we want. So whether 3 above and 3 below, 2 above and 2 below, 1 above 1 and below, 0.01 and 0.01 below, we need f of x to get as close to L as we want. Then what else do we need? We need a set of x values that allow us to move f of x as close as we want to L. Now note, this has nothing to do with what f of a is. F of a is not useful to us. We don't care about what actually happened to this point. For all we know, it could be undefined. For example, there's a hole in this function, okay? We need a set of x values that allow us to move f of x as close as we want to L. So think about it like this, okay? If we say that we want f of x to be within some epsilon of L, okay? We will either we can have it L plus epsilon or L below epsilon. What we need is we need x to be within delta of a such that for those x values, f of x will always be less than or equal to these epsilon values. Basically, effectively what we're saying is that no matter what epsilon values we choose, in other words, no matter how close we want f of x to be to L, we can always choose some delta value that will get us even closer. Okay? No, L plus epsilon is here, right? But the delta values will get us here and here, which are even closer than what our epsilon value wants. If we wanted L plus epsilon to be here, then we could get a minus delta and a plus delta there. No matter how we want it, we can get it even closer. That is effectively what the formal definition of a limit says. Now let's write the formal definition of a limit. Okay. For all epsilon greater than 0, okay, what is it? It just has to be greater than 0. Okay, the reason why it's greater than 0 is because to avoid confusion. It wouldn't matter if it was less than 0, given that we're subtracting and adding it. But the whole idea is that it can't be equal to 0, because once again, we don't actually care whether it is equal to L, and we don't care what happens at f of a. Okay, for all epsilon greater than 0, okay, there is a delta greater than 0 such that for all x that is within delta of a, f of x will be within epsilon of L. Now, that starts to seem something that is rigorous, that we can actually write into a formal definition. So what does that mean? Okay, if we want epsilon to be within L, there will always be a delta greater than 0, such that for all the x that is within this delta of this A, for all x within the delta of this A, f of x will be within epsilon of L. If you think about it, that makes sense, right? A minus delta, A plus delta. For all of those x values, okay, the y values are within epsilon of L, right? F of x will be within epsilon of L. Now let's write this into into a mathematical proof, okay? This already seems pretty mathematical, but let's finally write it into something that we can actually prove. And it's an actual definition, okay? For all epsilon greater than 0, there's a delta greater than 0, such that, okay, let me just erase all of this. Okay, you know what, let me keep it, such that for all x within delta of A. Okay, now let me write the formal definition below this, okay? For all epsilon greater than 0, there is a delta greater than 0 such that the absolute value of x minus delta, absolute value of x minus A, is less than delta, is greater than 0, okay? Is less than delta. In this, that arrow symbol means implies, okay? Such that 0 less than the absolute value of x minus A less than delta implies that the absolute value of f of x minus L is less than epsilon. Now that is the formal definition of a limit. And that is what this says, if you think about it, okay? And that is effectively saying this, okay? Now let's move on to a limit proof. So here we have the epsilon delta definition of a limit. And using that, we want to prove the limit as x approaches 4 of 3x minus 1 is equal to 11. Now, this seems kind of basic, right? Just plug in 4, you have 12 minus 1 is equal to 11. So that's how we can mentally check that this is in fact true. But we have to do a rigorous formal proof of this thing. Because like said before, the definition of a limit has absolutely nothing to do with the value of the function at that point. So we have to prove with this definition of the limit. So we need to find for this, okay, epsilon, so given this definition of epsilon, we should be able to find the delta for every epsilon, okay? So f of x in this case is 3x minus 1, use the red marker, okay, 3x minus 1. No, this is not the actual proof. Right now we're just trying to determine what delta is in terms of epsilon. 3x minus 1 minus 11 is less than epsilon. So what we're trying to do is that we've determined that this is for what the epsilon we're talking about is, okay? We need to now find that delta. Now how we need to find this delta is by somehow getting an absolute value of x minus 4. Trying to get that absolute value of x minus 4, and then using that, we can find our delta. Here's what I mean, okay? So now this means that you have 3x minus 12, okay, less than epsilon, or this means that you have 3 times absolute value of x minus 4 is less than epsilon, or absolute value of x minus 4 is less than epsilon over 3. So now, we know that the absolute value of x minus 4 is going to be less than epsilon over 3 if this is true. So what does that mean? That means that if we say that delta is equal to epsilon over 3, what we will have is that the absolute value of x minus 4 will be less than delta, okay, which will be greater than 0. So we will have that statement. We will say that the absolute value of x minus 4 is less than delta, which is equal to epsilon over 3, greater than 0. So given this statement, this must mean that this has to be true. And now we can trace our steps, okay? So in order for this to be true, let's multiply by 3 on all sides, and we get 3 times the absolute value of x minus 4 is less than, okay, less than epsilon, which means 3x minus 12 is less than epsilon, or 3x minus 11 minus 1 is less than epsilon. So what we've effectively done is found a delta in terms of epsilon that will always make it so that the f of x will be within epsilon of L. Okay? That's effectively what we've done. Now let me formally write this proof as to how you write it on a proof-based exam or something like that. Okay? Now, let epsilon be greater than 0. Okay? Choose delta to be equal to epsilon over 3. Okay? Now, 0 is less than the absolute value of x minus 4 is less than delta implies we don't need to write implies yet. So we have that 0 less than the absolute value of x minus 4 less than delta is equal to epsilon over 3 means that if we multiply by 3 on all sides, we have the absolute value of 3x minus 12. Now we can get rid of the 0 in this scenario because we're only concerned about what it's less than, not that it's greater than 0 anymore. So we have this less than epsilon. Okay, and this means this means that you have absolute value of 3x minus 11 minus 1 is less than epsilon. So 0 less than the absolute value of x minus 4 is less than delta implies that the absolute value of 3x minus 11 minus 1 is less than epsilon. So the limit as x approaches 4 of 3x minus 11 is equal to, 3x minus 1 is equal to 11. And that is how you do a formal epsilon delta proof of a limit. Now let's move on to some limit computations. And if you want to see some more proofs, I'll be uploading a video of that soon. And in that video, I'll also show the formal definition of a proof of a limit going to infinity. In other words, x approaches infinity, what does f of x approach? I'll give a formal definition to that as well, and I'll do some more proof examples. Now let's go on to some limit computations. Okay, so now let's do these limits using what we know about limits, okay? So find the limit as x approaches 0 of absolute value of x over x. Okay, as x approaches, so now one thing you really have to know about limits is that in order for a limit to exist, it has to approach that limit from the positive side and the negative side. And here's how we write that. What we mean is, think about it like this. If it approaches this point from this side, then we call that the negative side. From this side, we call it the positive side. So how we denote that using mathematical notation is the limit as x approaches 0 minus, like that, of the absolute value of x over x has to be equal to the limit for okay, as x approaches 0 from the positive side, absolute value over x in order for this limit to exist. The left and right limits have to be the same. Okay, so first let's find out the left limit, or approaching it from 0 minus. Okay, so as we get closer and closer to 0 from this side of things, think about it like this. Okay, for all x less than 0, absolute value of x is negative x. So for everything less than 0, this function is effectively negative 1. So as it approaches 0 from the negative side, this is equal to negative 1. And the limit, as x approaches 0 for the positive side, okay, of absolute value of x, think about it like this. Absolute value of x for all positive numbers is just x. So x over x is just 1. So this limit does not exist. And we write that as DNE, meaning just does not exist. Just shorthand notation, okay? Now, find the limit as x approaches infinity, 3x cubed plus 4x squared minus 7x plus 2 over 5x cubed plus 10x minus 5. Now, if you know derivatives, you can just do something called L'Hopital's rule. That's just like, you take the derivative of the top and the bottom. If the top and the bottom you go to 0 are both 0 or they're both infinity, but we don't know derivatives yet. So how can we do this? So think about it like this, okay? Whenever you see a rational function, always just divide both the top and the bottom by the largest power of x. In this case, it's x cubed. So and remember, we're doing the top and the bottom, so we're okay. Okay, x approaches infinity of 3 plus 4 over x minus 7 over x squared plus 2 over x cubed divided by 5 plus 10 over x squared minus 5 over x cubed. Now, as x approaches infinity, all these terms approach 0, right? 4 over infinity, that approaches 0. 7 over infinity squared, all of those approach 0. So what we're left with is 3 over 5. Okay, now let's do this. X squared minus 9 over x minus 3. Now, many people, as x approaches 3, many people would think, well, it's not defined at that point, which is true. There's a hole at that point. Remember, we don't care in a limit as to what the actual value is at that point. What we care is everything around it. And for everything around as x approaches 3, for everything around the limit at that point, this function is effectively equal to x plus 3. Because remember, we don't care about what actually happens at x equals 3. So that limit and this limit are the same. So what we're left with is the limit of x plus 3 as x approaches 3, which is just 6. Okay? Finally, we have this, okay? Now, this looks like a pretty familiar limit to people who've done like calculus. No, we're not taking x to 0. We're doing as x approaches infinity, sine of x over x. Now, there's no real way to there's no way that you can just say, well, we can prove that this is the answer unless you know like more advanced mathematics. But for this one, you just have to think about it for a little bit. As x approaches infinity, sine of x will always be between negative 1 and positive 1. And x will approach infinity. So if the denominator approaches infinity and the numerator is always bound within some range, then the fraction has to approach 0. It just gets smaller and smaller and it approaches 0. Now, no, these are limit computations. We're not proving any of these. If you want to, you can prove these. But for some of these, you need to know the proof on what happens as the x approaches infinity. What is the formal definition of a limit at that point? In order to do that, stick around for my next video where I'll explain the formal definition of a limit that approaches infinity. And finally, okay, check out the description for my website and check it out for a worksheet with more limit questions and more limit proofs. Thank you for watching this video, and next week I'll upload a new calc vid. Thank you. Bye.